Okay, thank you everyone for joining this SimScale workshop on fast and easy electronics thermal management. It's good to see so many of you here, so let's make a start. If you've got any questions as you're going through, you can ask the questions using the questions functionality. Okay, so first of all, I'll introduce myself and introduce David, who's going to be the star of the presentation today. So hi, I'm Steve Lene. I'm one of the application engineering managers here at SimScale, and David's going to be the star of the show today, doing the hands-on workshop. David's one of our senior application engineers, and he's got a marine engineering background and experience of working in the CAE industry.
Exactly. Hello, everyone. I know a few of you already, and so I look forward to taking you through this workshop and showing you the ropes on SimScale a bit. And we've got a really exciting application, and I look forward to getting into it. So back over to Steve for now.
Great. Thanks, David. So what do we do here at SimScale? Well, we created the world's first cloud-based engineering simulation platform. And the fantastic thing about this platform is it's all accessible through your web browser. And you can use the platform to do fluid dynamics, solid mechanics, and thermodynamics, all from a cloud-hosted system. So for this workshop, how do you get the most out of it? Well, the best thing to do is to actually just follow along with David. He'll be using milestones to guide you through the different steps. So the milestones will be in the tree structure down the side of the software. And if you get lost or lose your way, you can just skip to the next milestone and you'll be at exactly the same step. Ask questions as we go through. You can use the questions functionality, and I'll be fielding the questions. If there's something urgent that should be addressed to all of you, I'll interrupt David and we can have that live. But otherwise, we'll leave it until the end and we can have a Q&A session at the end. By the end of it, you'll have a working simulation set up, and that's the great thing about this session. You'll be able to come back to it, you'll have results, and you'll have a template that you can use for your future simulations. We recommend that you use a second device or a second screen so that you can follow along easily. This could be a tablet or another laptop or simply a second screen. And we also recommend that you use an external mouse for manipulating the model. Okay, that's all from me for an introduction, and I'll hand over to David now. Thanks.
Awesome. Thank you very much, Steve. Okay, so I hope that all of you are within the industry or have some interest in the LED, in the lighting industry, or in electronics cooling in general. So this workshop is really going to showcase the capabilities of SimScale as a design tool, and the specific application we'll look at today is a passively cooled LED module. So we've essentially got the LED package on top of a PCB board, and then we've got a large radial heatsink, and we want to really understand the cooling capacity of that heatsink. So as I said, the full cooling is passively cooled, so we're relying on buoyant effects rather than having forced convection with fans or something like this. So we're going to be purely looking at a passively cooled LED module, and a big part of passively cooled modules is their ability to radiate heat as well as to develop the convective cooling through the buoyancy effects. So what we're going to do is we're going to look for optimizing the material selection of the heatsink with regards to radiative cooling. So we can test out 3 different heatsink material types and see what is their effect on our result of interest, which in this case is the LED junction temperature. Okay. So the questions we're going to ask, I've already explained one of them. We're looking for that junction temperature, and is it going to be within the operating range for the different materials firstly, and then what is the optimal choice of material? What is the minimum LED junction temperature that we can get down to by just varying some of the material properties? So this is really going to show SimScale as a design tool. We're going to run a full design study together, and yeah, in the end, you're going to have a template for your simulations. You're also going to have the results of this workshop that you can go away and look at later as well. But we'll have a quick look at them all together as well. So the agenda, the milestones, so Steve already mentioned that we're going to split our project into milestones just to make sure that everyone can follow along nice and easily. If you miss one milestone, then you can catch up when we get to the next one, and you can just start milestone 1 with everybody else, for example. So milestone 0 is going to be actually using SimScale's CAD functionality to modify the LED module geometry and get it ready for a CFD thermal analysis. Milestone 1 is going to be defining the physics of the situation that we want to have being simulated. So we want to ensure that gravity is enabled, which will enable the buoyant effects and the natural convection cooling. We're going to enable radiation, and then we're going to assign the materials. Milestone 2 is going to be defining operating conditions. So what is the physical scenario that we're trying to replicate? In reality, we can define that using the boundary conditions, and we're also going to define the power source of the LED package itself. Finally, we'll run a design study all together, so you will see SimScale's parallel cloud computing in action. You're going to feel the power of cloud computing, and then we'll run 3 different simulations all at the same time, and then we'll be able to compare the results from those 3 different simulations and get that design feedback from the simulation iterations. Finally, we'll have a look at the results themselves in the 3D post-processor, and then we can also open up the floor to a discussion about those results, because I really want to make sure that they are the results that would bring value within your design cycle. And yeah, so without further ado, I would like to get started on the workshop, and so please feel free to ask questions via the text functionality, and let's get started.
I'll just send out the link to the project now on the chat functionality in case you haven't received that from the joining instructions.
Okay, Steve, have you already sent that out now?
Yes, that's gone.
Perfect. Okay. So let's get started. You've all been provided with the link to this SimScale project landing page, and I'll pause here for just a second so that everyone gets to the same point, and then we can get started with the workshop. So once you've reached the landing page, I would like everyone to take a copy for themselves of this project. And the copy button's found up here in the top right. So you can copy the project, you can rename it, for example, with your name, and hit the copy project button. This is going to give you your own copy where you can be the owner of the project, make your own edits, and follow along with the workshop. It will also be a useful template for your future simulations with SimScale. So once you've copied the project, you'll be redirected to the SimScale workbench. And then once you've reached the SimScale workbench, then you will see the project that we're going to complete today. We've split the simulation into a number of milestones that we've already discussed in the introduction. And what I would like you to do is navigate to the geometry tree where you'll find milestone 0. If you click on milestone 0, this will bring up in the viewer the geometry of the LED module that we are going to simulate today. Now, the first thing that we want to do is we want to prepare this model for simulation. Now that can be done using SimScale's own CAD functionality in CAD mode, which is found with this little button here next to the geometry. So then everyone can enter the CAD mode and we can get started with preparing the geometry for simulation. Once you've entered the CAD mode, you'll be able to visualize the model just like in the workbench, and then we can get started. So what we want to do is create the air volume, the air space around our heatsink. This can be done with a flow volume. So we go to create, flow volume, external. So we're going to create an external flow volume of air around our radial heatsink LED module. We're going to stick with the default air volume sizing and hit apply. There you can see that the volume has been created now as a CAD volume over on the geometry tree on the right hand side. We can hide that flow volume by clicking the hide button, the eye icon. The next thing we want to do is we want to do an imprint operation. This allows all the interfaces between the solids, between the solid components and the solid and the fluid space. This allows for perfect alignment between these interfaces, which is going to allow for accurate heat transfer across them. So the imprint operation is found under Model, Imprint, and we can go ahead and hit Apply. Okay, so that's all we needed to do in terms of CAD preparation for this CFD thermal analysis. If you want, you can change the Now, once we've got to this point, we can hit the Finish button and we're going to be redirected to the simulation workspace. Now, our modified geometry enters the SimScale workspace as a copy of the original. And there it is. If we want, we can change the visualization to make it transparent, so that we can see a little bit better of what we're doing. Now, the last step in milestone 0 is to create a simulation. So we're going to hit this Create Simulation button, and that takes us to the simulation library, which shows all the different types of analysis that we can do on the SimScale platform. So this goes from fluid-only analysis to coupling between fluids and solids, looking at thermal analysis, and also to pure structural analyses as well. But for today's session, we're going to do a full thermal management simulation that takes into account conduction within solids, convection within the fluids, and also radiation between the surfaces in the model. Now that can be achieved all together in a single simulation called this conjugate heat transfer. So if you select the conjugate heat transfer version 2.0 and hit Create Simulation, we're then going to generate the simulation template. Now this goes for all analysis types in SimScale. You get a template that is going to help guide you along your way to getting a successful simulation. You'll notice the first step it's doing is finding the contacts, finding the interfaces between the solids and fluids and all the different components within the model. So that's a purely automatic feature, and that is going to enable accurate heat transfer between the components. You'll notice in the template, it's essentially a checklist of things that need to get done before your simulation is ready to start. A lot of that is already taken care of by SimScale's smart default settings, and then all we need to be concerned with are the actual design parameters and the physics that we want to bring into the simulation. So that brings us to the end of milestone 0. Now we can minimize that simulation template in the simulation tree, and we can go to milestone number 1. So I'll pause here just so everyone has a chance to catch up. Now in milestone 1, we are going to be defining the physics of our simulation. So there are a few key points that we want to bring into the scenario so that we're accurately representing the real world. Namely, we want to enable radiation within our simulation, and that can be done by clicking on the simulation settings, which is really achieved by selecting the simulation name here. And we can toggle on radiation in the simulation settings. Hit the Save button. And then we've enabled radiation already. The next thing we want to ensure is that we have gravity acting in the correct direction. So under Model, we can then assign the direction of gravity. In this case, we would expect the gravity to be working in the negative Z direction. So gravity is pulling down in this direction, and that is going to enable the heat to rise above the heatsink, causing effective passive cooling of this LED module. So let's add the magnitude and direction of gravity into the dialog, and we can hit Save. Okay, so we have radiation, we have gravity, which is going to enable those buoyancy effects and the passive cooling in terms of convection in the simulation. And now what we want to do is assign the materials. So under materials, we're going to assign the fluid. We're going to assign it as air. Now this can be done from the material library, hitting the plus button next to fluids and applying air. Okay, and once you have air in your simulation, then you can apply it to the flow region that we created in CAD mode. Now you'll notice that this is the default air material, but any of the parameters can be varied and saved for your next simulations. Now under solids, let's go to the solid material library on the plus button next to solids. And we want to bring in, first of all, aluminium, which we're going to use to model the heatsink and, for simplicity in this case, the PCB board as well. So we can select either from the geometry tree or from the viewer itself. After hiding the flow region, we can select the heatsink and the PCB. I'm just going to change the render mode here and hide the flow region so that we can see what we're doing. Okay, so we've got the heatsink and the PCB board only selected, and then we can hit Save. For modeling the LED itself, we're going to use standard silicon material. Now we have more advanced features for modeling LEDs in more detail, but in this simulation we're only really concerned about the heatsink performance, so we're going to keep the LED package as simple as possible. But just so you're aware, we can also model these LEDs as thermal network systems, which would be based on the LED manufacturer's data sheets. So you have those options for bringing in more accuracy in terms of modeling the LED as well. But in this case, we're just going to model it as silicon for now. Now, the aim of this simulation is to optimize the material selection for the heatsink. So now I want to create a few extra materials that we can then use in our design study. Firstly, I want to create anodized aluminium. So if we go to aluminium again, that's going to be the standard aluminium. And what we can do is we can then adapt the emissivity of the aluminium material to make it correspond with those properties of anodized aluminium. So the emissivity, so the tendency of the material to emit radiant heat, would be 0.7 for anodized aluminium. And we can hit save there. And that's going to be saved for our design study. Lastly, I want to create one more. So back in the solids material library, let's select aluminium again. And this time we're going to set the emissivity to 0.95, which is equivalent to standard aluminium, but with a radiative paint. Okay, so we've got our 3 types of aluminium that we're going to test out. I just want to make one final adjustment. So in our standard aluminium here, this is based on rough aluminium, which is unlikely to be used in the heatsink design here. So I would make this to 0.3, which is the equivalent of sort of polished aluminium. Okay. So now we've got all of our materials defined in the simulation. And that means we've finished milestone 1. So well done, everybody. We can move on to milestone 2, which is where we're going to define the operating conditions of the simulation. So everyone can minimize milestone 1 and select milestone 2. So the operating conditions are controlled by the boundary conditions and the advanced concepts that we can bring into the simulation. So boundary conditions we're going to apply to the flow region on the external surfaces. So let's unhide the flow region. And we're going to use what's called natural convection inlets outlets. These boundary conditions allow the air to enter and exit the domain, and when it's entering, it's coming in with a defined ambient temperature. So we're essentially modeling the LED module in a large space of air. I'm going to also put the far field temperature to the same as the ambient temperature. So let's select the 6 external faces of the flow region. And hit save. Next, we're going to add the power to the LED package itself. Under Advanced Concepts, we can go to Power Sources, hit the plus button, an absolute power source. And we're going to add a 10-watt power source to the LED itself. So we can either, again, select it from the geometry tree or hide the other parts and select it in the viewer. So there we've assigned the absolute power of 10 watts to the LED package. And that brings us to the end of milestone 2. We can minimize that and get into the exciting bit, the running of an actual design study where we can then test between the different materials and optimize the selection. So everyone can then jump to milestone 3. And I'll pause here again for just a second to make sure that everyone's got to the same point. Okay, so up to this point, we've defined the design parameters of our simulation. So we've enabled the physics and we've set the operating conditions. And now what we want to do is set off a number of simulation runs in parallel, making the use of parallel cloud computation. And this is really how our customers benefit from SimScale as a design tool. So you can run all these different design variations, different material selections in parallel, and get your results back at the same time, and then compare between those simulation results in order to optimize design and help reduce costs within the design cycle as well. So let's start the simulations. Our first simulation is set off to run with the standard aluminium material applied to the heatsink. So we can then go to the plus simulation run here, hit the plus button. We're going to ignore this warning, which is just saying that there's some unassigned settings, but those are the materials that we've created anyway. So the anodized aluminium, and the radiative paint. And we're going to say run anyway. So this is going to be run 1, and we're going to name it aluminium. There we can hit start. So we can see that the simulation process has started. Firstly, it's computing a mesh using our default automatic meshing settings. And secondly, it's then going to start the CFD run itself. Now, whilst that's happening, we can already start setting off our next simulations as well. So let's go back to our material definitions up here. Select the aluminium and remove the heatsink from the aluminium material definition. Let's go to anodized aluminium and select the heatsink. We can save that there. And we can already then set off our next simulation within this design study. So let's call it run 2, anodized aluminium. And we can hit start. Now we can use the same process, go to anodized aluminium, clear the list or hit the cross button, and then go to the aluminium with radiative paint and assign that to the heatsink. And then again, we can set that simulation off and run. Aluminium with radiative paint is going to be the name for this one. Then we can hit start. And it's as simple as that. So we've now set off 3 simulations in parallel, and we're going to be able to then get design feedback once those results come in. So we're not going to wait for the simulations to finish during this session. I've already run a design study that we can then take a look at the results together. So if we minimize milestone 3, and I hope everyone's now achieved milestone 3 as well. And that means that then you're going to have the results within your account to this design study that you can then have a look at later on after the session, or you can follow along with me and do some post-processing right now. So we finished milestone 3, and then we can go to the finished design study and post-process the results together. So under the simulation runs, you'll see the 3 simulations that we've set off already. And then you can see the runtime. So taking nearly 1.5 hours and at a compute cost of 46.9 or 47 core hours. We can then go to post-process the results to take a look at the 3D results, and then we're going to extract our result of interest, which for obviously LED designers, manufacturers, we're interested in the LED junction temperatures. Now you should see the post processor where we can then manipulate and analyze the 3D simulation results for the LED module. And we can go in and really inspect those features of interest and understand how effective the heatsink actually is at cooling this LED package. So what we're going to do for that is use the bulk calculator. We can toggle that on the top right over here. And we can select the LED. Now that gives us then a readout of the maximum, the minimum, and the average temperature for the LED itself. Okay, so we can see that that is pushing up to about 60 degrees Celsius. Now that's with the standard aluminium heatsink. Now what we can do is we can jump into run 2, do exactly the same thing, and compare how much more effective the heatsink with anodized aluminium is at cooling the LED package. So we would expect with a material that has better radiative properties, a higher emissivity value, we would expect to see more cooling effect thanks to that radiative cooling. Again, we can select the heatsink and we see the average is down at 57. So that's already 2 degrees of difference just by having a different material property in terms of the emissivity of that material. So this is quite interesting. No design changes have been made here in terms of the actual geometric design. We've still got that same radial heatsink, but just by changing the radiative properties, then we're seeing a couple of degrees of difference in the cooling capacity of the heatsink. Finally, let's post-process run 3 together in exactly the same way. Select the LED, and there we have 56 degrees C. Okay, so we're going from aluminium, standard aluminium, polished aluminium of about 60 degrees C, and we're reducing down to 56 degrees C by just testing different materials. And in that way, we can really optimize the material selection. I will jump back to the slides now. I've put those results together, so then we can see the side-by-side comparison of those 3 simulation runs. So it's really a marked difference of 4 degrees by just testing different materials with different radiative properties. So hopefully that provides an example of how you could use SimScale as well to help optimize your designs and reduce costs of prototyping failures and help really bring simulation into your design process. So I really want to congratulate everyone. If you've got to this point, then that's the end of the workshop. You've managed to run or set up a full simulation project in 25 minutes or so. Now I would open the floor to questions, and please fire away. I believe there's already some questions that have come through by text, and myself and Steve will do our best to answer all of them in the time that we have left.
That was really great. Thanks, David. We've got some questions come in to answer. So let me just pull those up and we can start going through them. Please feel free to ask any more questions if you've been busy following along and you've jotted down a couple of questions that you'd like to ask. Please do type those in the questions functionality and we'd be happy to answer those. So David, one question that's come in is around parallelizing simulations, and someone wants to know how many simulations can be run in parallel.
Absolutely. So in terms of the actual scalability of SimScale as a solution, there really is no boundary to how many simulations you can be running in parallel. So the solution really scales with your need for simulation and allows you to run, if you have 5 different materials that you want to compare, if you have 5 different design candidates, so different geometries that you want to compare, you can be running them all at the same time. So the different operating conditions, the different material selection, the different geometry itself, that can all be simulated in parallel. The only limiting factor is going to be the actual amount of compute power that you have associated with your license, because we put a cost on the simulations that you're running because you're using these remote servers to run them, and then yeah, so as long as you've got the compute hours in your account, then there's absolutely no limit to the number of simulations you can be running in parallel.
That's great, thanks. So another question that's come in is around the post-processing and whether you can download the simulation result as well.
Absolutely, yes. If you want to take your full data set, store it locally, then you can absolutely do that. And it's also in a usable function for many third-party post-processing tools. For example, you can go away and use another post-processing tool if you wish. But yeah, all the results that you compute on SimScale are fully downloadable as well.
Great. Yeah, please keep the questions coming. We've got another one here, David. Someone's asked, how can we set up the conduction between the materials? For example, I want to put the thermal grease between the PCB and the heatsink. How can we set that up?
That's a really good question. So I hope everyone can still see my screen. I will jump back to the project. Can everyone still see my screen?
Yep, I can.
Fantastic. So let's look at the final design study that we've already run. And if you wanted to add an additional, you don't want to explicitly model the thermal grease itself, but you want to have the conductive effects of a thermal grease. What you can do is then, for example, between the PCB board and the heatsink, if we select those 2 materials, then we can filter the contacts by selection. So we're going to find the interface between those 2 parts. And then what you're able to do is model that as a thin layer resistance interface, and we can add the layer thickness and we can add the thermal conductivity. So this is really useful if you've got very, very thin components or things like adhesive tape or glue, things like this that you don't explicitly want to model in your geometry. You can then have the effects of those conductive interfaces simulated via a thin layer resistance model, just like this. Okay.
Okay, that's a great answer. Very thorough. Thanks, David. Another question's come in about how do you measure convergence of a simulation? Can you see convergence?
Yeah, absolutely. So let's stay in the platform. Let's have a look at the actual runs that we've computed here. So there's a number of ways to look at convergence. Firstly, you've got, for example, the residuals themselves. So these are the more sort of mathematical measures of convergence, and you get plots of your residuals generated out during the simulation. But what's maybe more important is to actually look at physical values. So here, what I've actually done in these simulations is added a result control, because I always like to check that my simulations are really converging, so that the physical temperature of the LED has stabilized. So that's really important to give you confidence that your simulations are converging on a realistic value, not just some numerical growth and reduction in the value. So I like to track my result of interest, namely the LED case temperature. So this is the LED case temperature during the simulation, and we see that by the end it's stabilized onto that final value. So I think that's the most important way to test convergence, is to understand the oscillations and the development of your actual result of interest as well.
Yeah, that's great. And you can obviously monitor these things live as your simulation is running as well. So if you want to monitor for convergence and stop a simulation early to save on core hours, you can certainly do that. Okay, so we've got a few more questions to get through. One that's come in is, how do you use the probe function to check the temperatures at a specific point?
So there's two ways of doing this. There's the predefined probe points that you set up before a simulation that can be done using result control. So you add a probe point, for example, in the same position as your thermal couple in a benchmark experiment, and otherwise you can do it in the 3D post-processor itself, and that's more of a qualitative approach where we just can pick and choose whatever we're looking at, and I can show you that here. So if we jump back into the actual 3D post-processing, because I didn't set up any fixed probe points before setting off these simulations, but you can absolutely do that, and I would recommend that if you're comparing against experiments where you've got your thermal couples in specific locations, because then you've got real control over that output value. But if you want to be a little bit more haphazard and just sort of inspect your model on point-wise basis, you can use the point select tool here, inspect point, and then that will show you the temperature values at any point that you select in the model. Okay.
Excellent. So we've got a few more comments coming in, but they're all thanks for such a good presentation. So if no one else has got any actual questions, I think we'll close it soon. So we'll just leave it for a couple more moments in case you've got another question. But thank you for your positive comments. Okay, great. I think we'll close it there, David. Thank you very much for the presentation and for running such a good session there for everyone to follow along. Thanks, everyone.
No problem at all. Good fun. Thank you very much. Bye-bye.